Hello everybody. I wanted to take the time today to put together a video describing the practical applications of hybrid orbitals in organic chemistry. As you've likely read in your textbook, the hybridization of orbitals is really a mathematical way to explain the behavior that we see in nature. The classic example used in most textbooks is that if you look at a methane molecule with the formula CH4, that all four of those carbon-hydrogen bonds are similar in nature. They're all of similar length, similar strength, clearly made by the exchange or the sharing of electrons in a similar way between the carbon and hydrogen. So one question that is frequently asked in this sort of setting is to identify an orbital, or which orbitals are responsible for a particular bond in a molecule. And that's what I mean by a practical approach. You can read in the textbook all about how atomic orbitals don't exactly solve this problem, how the concept of hybridization was described by Linus Pauling and refined by others. It's a mathematical treatment that, frankly, is well beyond, the mathematics are well beyond what we need to worry about. What we want to think about here is what is a hybrid orbital and how does that affect me? So we'll use methane as an example here for a moment. Basically, the idea here, if we think about what that carbon looked like as an atomic, from the atomic scale, we could say that its electron configuration, remember these from general chemistry and early organic, its electron configuration looked like that. And basically what we do here when we talk about hybridization is we say we're going to take those valence electrons. Remember, valence electrons are those in the highest numbered electron shell, so level 2 in this case. We're going to take those valence electrons and repurpose some of them, or essentially change the way that we're thinking about some of those. So instead of imagining that I have 2 electrons sitting in my 2s orbital and 2 electrons sitting in my 2p orbitals, one in each of those 2 degenerate orbitals, I'm going to think about the ability perhaps to promote or to excite one of those electrons up into this p orbital. And more than that, I'm going to think, well, how can I reimagine combining these mathematical spaces around the atom? Right? Orbitals at their core are just a mathematical description of where an electron is likely to be, which space around a nucleus that electron is likely to occupy at any given time. So what we're going to do when we talk about hybrid orbitals is we're going to take these and essentially combine those together, run them through this, what I like to call a hybridization machine, this mathematical transformation to say, now, instead of having a single s orbital and 3 p orbitals, I have the possibility of having up to 4 what I would now call sp3 orbitals. Now notice that the name here comes from the fact that I put in 1s and 3p orbitals into the machine, so to speak. So I've put in 4 orbitals, I get out 4 orbitals. Right? They're defining space around the nucleus, and so I can't just routinely create space or delete space. The space is there. I'm just changing the way I describe it. So what I have with a carbon atom in this sense is that I now have 4 valence orbitals, these 4 sp3 orbitals, and these would be considered level 2 sp3 orbitals, if you want to get back to that, valence shell sort of a description. And I have my 4 electrons in there. I had 4 electrons in the valence shell before. I still have 4 electrons. What this affords me, though, is the opportunity to put in 4 additional electrons there in equally energetic spaces. So the outcome here is that bonds made with those 4 hybrid orbitals will be identical to one another. They'll be of similar shape, strength, length, that kind of thing. Okay. just by way of shapes, while we're mentioning shape, you may remember from the first times that you saw atomic orbital theory that an s orbital is sort of a sphere around the nucleus, and that a p orbital is sort of a dumbbell shape with a positive and a negative lobe, whether it goes left to right, front to back, top to bottom, relative to the nucleus. It looks something like that. So it turns out when you put those two mathematical equations together and you do the math that's required here, you end up with an sp3 orbital that looks kind of like this. So it's got a bit of that dumbbell shape to it, but it's definitely asymmetrical. And if I were to consider all four of these hybrid sp3 orbitals together, I would end up with a situation that looks a bit like this. Okay, one to the other side a bit, and one pointed sort of forward and backward a bit. Now, I hope that you appreciate the difficulty of drawing in 3 dimensions on a flat page, but basically what we end up with is a tetrahedral structure. I have the nucleus in the middle, and I have 4 directions, which you've seen in your textbook, can be represented like this. Those 4 spaces, those 4 hybrid orbitals around that central nucleus are equally spaced from one another, and that affords us, in 3-dimensional space, about a 109-degree angle from one to the other. Okay, that's our classic tetrahedral shape. So, when I talk about a particular methane molecule like this, if a question were to say, look at this highlighted bond here, or in fact any of these bonds, right? What orbitals are involved in making this bond? Well, I would say that carbon is the one that's going to potentially hybridize. Hydrogen can't do this, right? It's too small. Hydrogen only has a 1s orbital. And so we can maybe cheat and say the hydrogen 1s orbital for sure is involved. What about carbon? Well, the easiest way to look at this is to say how many electron bonding groups are, not even bonding, how many electron groups are there around the central atom? In this case, I've got the one that I highlighted there in blue. I also have 3 additional electron groups around that central carbon atom. And so if I want to have 4 groups of electrons around a central atom, I'd better have 4 orbitals to accomplish that. And if I want to have 4 hybrid orbitals, those orbitals have to be sp3, right? That's the result of combining together an atomic s orbital with 3 separate atomic p orbitals. And that's where that 3 comes from. So each of the bonds in methane is built, if you will, by the overlap of hydrogen's 1s orbital, like this, and methane's, I'll draw it in red, methane's sp3 orbital like that. And so it's the electrons spending time in here that are going to cause that association between those 2 atoms. I'd have the same thing pointed towards each of the other 3 hydrogens in the molecule. All right. We have a similar situation when we talk about other molecules that you may have learned in Gen Chem are tetrahedral frameworks, or what we may have called a tetrahedral electron geometry. Ammonia is one of those molecules. Water is another. And so I'm drawing these best I can with the appropriate sort of shape. All right. In a Gen Chem sort of a discussion, you would have looked at these and said, okay, there are 4 electron groups around that central atom, the nitrogen or the oxygen. And so that means that I have tetrahedral electron geometry. We would have said that the angles are roughly 109 degrees, although they're a little bit smaller for these molecules. Now, in terms of hybridization, what's the hybridization of the nitrogen in an ammonia molecule? Well, if I think about what this looked like, I still have 4 electron groups around that central nitrogen. So nitrogen's electron configuration from an atomic standpoint would have looked like this. right? 1s2, 2s2, and then as I start to count across, I'm going to end up with 2p3 for nitrogen. 5 valence electrons right here in level 2. So I still have the same atomic orbitals if I want to think about those. I just have one extra electron in there. So if I'm talking about hybridizing, it's the same kind of a setup here. If I put these together, nitrogen will still have 4 hybrid sp3 orbitals. Again, these are in level 2, so I could label them as 2 sp3 if I wanted to. I have 5 electrons that were in those orbitals to begin with when I thought about them from the atomic standpoint. I'm going to have 5 electrons filling these orbitals in the hybrid standpoint as well. And just like in the atomic case, you'd put 1 electron in each orbital before doubling up where you need to. And what we can see now is exactly what nitrogen is capable of doing, and what it's in fact doing in the ammonia molecule. I have right here a pair of electrons in an sp3 hybrid orbital. That's that pair right there. And I have 3 singly unpaired electrons in the sp3 hybrid orbitals. That's going to make up 1, 2, 3 bonds in that molecule. And so again, if I were to label what hybrid orbitals went into this, I'd say the nitrogen has sp3 hybridization. And what I'm looking at here is an sp3 hybrid orbital from nitrogen overlapping the only thing hydrogen has is a 1s orbital. Okay? In this case, the geometry is similar to that of methane up above. It's just that one of the hybrid orbitals has an electron pair in it. The other 3 hybrid orbitals are overlapping with other atoms to make bonds. And the same thing is true for oxygen down below. Right? If I were to look at the same kind of a setup, here's an oxygen, 1s2, 2s2, 2p4 now. Those valence electrons in the atomic sense would look like this. Right, I have 6 valence electrons altogether. If I feed those into Linus Pauling's hybridization machine, I spit out my 4 hybrid orbitals, and those same 6 electrons are in there. 1, 2, 3, 4, 5, 6. And notice what I have now. I have 2 lone pairs of electrons in those hybrid orbitals, right here. And I have 2 unpaired electrons that are left to bond with something else. And so I would say that's an oxygen sp3 orbital overlapping with the only thing hydrogen has to give, a 1s orbital. All right. All 3 of these are what we would have called in Gen Chem a tetrahedral electron geometry. And that, for all practical purposes, is equivalent to saying it's an sp3 hybridized orbital, or hybridized atom, okay? So you can put those 2 ideas kind of together in your head. What you learned in Gen Chem for tetrahedral, now you can call it sp3 hybridized. So what about sp2 hybridized? Well, sp2, as the name suggests, tells me that when I combined together my s and my 3 p orbitals, right, those come as a set. When I combine those together, notice the name, sp2. That means I took this one and this one and this one and combined them together. And so here's my hybridization machine. 1, 2, 3 of those sp2 hybrid orbitals. And what's left? Well, I had 4 orbitals to begin with. I'd better have 4 orbitals when I get done. And I do. That 4th one is a p orbital, left over from the atomic orbitals. One way to think about this is in a very functional way, to say I didn't need them. Remember, this is just a mathematical calculation I do to figure out where electrons are and how I want to represent them. One way to think about it is to say, in order to accomplish the structure I'm looking at, I didn't need them. Essentially, I only needed 3 equally spaced electron groups around the central atom. And so I can do it this way. A classic example of this would be, for instance, a carbon taking part in a double bond with something else. So let's look maybe at the molecule of, oops, why did I do that? I apologize, just a moment. Let's look perhaps at the molecule ethene, which has this structure. And let's do the same sort of a question. Which orbitals are involved in making each of these bonds? Well, we're going to look at each one of those carbons, and they're both the same, right? It's a symmetrical molecule, so I'll just look at one of them for right now. I'm going to say I've got 1, 2, 3 electron groups around that central carbon. Okay, 3 groups of electrons, spaced equally. In Gen Chem, we would have used the language here to say that this has a trigonal planar electron geometry, and we would have said that the angles are about 120 degrees. And that's still true now, right? Nothing changed. It's still true. But in terms of hybrid theory, we want to think about it here. Well, what do I need to make those 3 electron groups? Well, I'm going to need what I've just drawn up above. I'm going to need to think about combining or hybridizing an s orbital with 2 of the p orbitals so that I get the 3 equivalent electron groups around that central atom. All right, and so when I look at a molecule like ethene, what I'm going to say is I have several different sort of distinct types of bonds. And I'm going to elaborate this out just a little bit. Okay, I'm going to just blow up some of this and say I've got a hydrogen going to carbon, going to the other carbon, and to a hydrogen, right? And I only drew it bigger so that I can label this better. Remember, hydrogen only has a 1s orbital. That's all. So we know hydrogen's contributing its 1s orbital to every bond. In terms of carbon, we can now say, I know I have an sp2 hybridized orbital there, there, and there. Okay. Similarly for the other carbon, maybe I'll pick a different color. Let's go with orange. sp2, sp2, sp2. Right? I needed 3 equivalently spaced, equivalent energy bonds or orbitals to make bonds around this central atom. And so that's it. Now, what that means is that for the hydrogen-carbon bonds, I've got an overlap of hydrogen's 1s orbital with a carbon sp2 orbital. And the same would be true on the other side, all 4 of those hydrogens, in fact. For this first bond between the 2 carbons, I've got my red carbon sp2 orbital overlapping with my orange carbon's sp2 orbital. That's going to form the first bond, or what's called the sigma bond. Sigma is just the first bond between any pair of atoms. Okay? Single bond between any pair of atoms. So the hydrogen-carbon bonds here are sigma bonds. One of the carbon-carbon bonds is a sigma bond. What about the other one? Let's go with a crazy color on this this next one. Let's go with purple. So what about this bond here, this other bond, the second bond? How is that thing being formed? Well, we've already used our 3 sp2 hybrid orbitals. This is an overlap of that p orbital from each atom, that one that we left over from each carbon. And so that second bond is a result of a carbon 2p overlapping with the other carbon's 2p orbital. And this second bond is what's called a pi bond. And so pi bonds are just any subsequent bond, not the first one, but a second bond or a third bond between a pair of atoms. So what we know about these bonds is that technically, because they're formed by this p orbital, it's a little bit higher in energy than the hybrid orbitals. I maybe should have drawn it up just a little bit on this diagram here. Let's stick with our purple. Let's move him up just a little bit in energy relative to the sp2s. Those are the bonds that are typically going to react. So in organic chemistry, when we get into all the reactions of alkenes and alkynes, these double and triple bonds, it's typically going to be those pi electrons, the second or third bonds, that are going to react first. okay? So in terms of questions you could see about a molecule like this, what orbitals are being overlapped to form the bond? So we've got our hydrogen 1s with our carbon sp2s. In the center, we've got a carbon sp2 sigma bond, and we've got a carbon 2p pi bond. So some questions might ask you to count the number of sigma bonds or the number of pi bonds or to identify particular orbitals. This is the kind of thing you'd be doing. Another classic example when we talk about sp2 hybridization would be a molecule like formaldehyde. Okay, formaldehyde looks like that. And so we could say, well, what is the hybridization? Again, well, let's look at it in terms of carbon. Because remember, hydrogen only has 1s orbitals. That's it. So what about carbon? Carbon here has 3 electron groups around the central atom, around the carbon. So I've got 1 electron group there in red, 1 electron group there in red, and then the bond up to the top, I'm going to highlight one of those, okay, going up to the top. That electron group at the top, we now know, just like we saw with ethene, that's going to be 2 distinct types of bonds. So what carbon has going for it is sp2 hybridization. It's 3 electron groups, sp2 hybridized. What about oxygen? Let's look at oxygen. We'll make oxygen purple here. Oxygen has 1 group from that pair of electrons, another group for that pair of electrons, and this group that's bonding to carbon. 3 electron groups. That means oxygen is sp2 hybridized as well, right? And so when we think about what's going on here, carbon's got 3 sp2 orbitals, oxygen's got 3 sp2 orbitals, and that leftover p orbital over there. Hydrogen's got pretty much nothing, just its 1s. And so what are we talking about as far as the bonds go? Well, what we know here now is that both carbon-hydrogen bonds are going to be hydrogen's 1s orbital, because that's all it has, overlapping with an sp2 hybrid orbital from carbon. When we talk about oxygen up top, oxygen's lone pairs of electrons are in hybrid orbitals, right? Both of the lone pairs. And that sigma bond between carbon and oxygen is the result of those hybrid orbitals overlapping. The other one, the pi bond, the second bond, that's going to be the oxygen 2p orbital overlapping with carbon's 2p orbital. These guys over here. This is going to form my pi bond, and I've got my overlap here to form my carbon-oxygen sigma, my lone pair of electrons sitting in those, and my overlap here to form my carbon-hydrogen sigma. In fact, I have 2 hydrogens, right? So maybe I'll draw 2 of them. This guy's overlapping here. So anytime you see a central atom with 3 groups of electrons, or what you would have called in Gen Chem a trigonal planar or 120-degree angle sort of a molecule, that's what we're going to say now is sp2 hybridized. It's just a different way to think about it. The last kind of hybridization that we're going to talk about in organic is sp hybridization. And hopefully by now you're screaming at the screen saying, Stamper, I know this is going to be 2 electron groups, right? Yes. So instead of having an s and 3p orbitals in the atom, we're going to use Pauling's hybridization machine to crunch these together and say, I've got 2 equal intensity hybrid orbitals. The naming here is going to be an s and a p, and then I still have my 2 p orbitals left over. All right, so essentially I took one of these and hybridized them together, and I left the other 2 alone. This is going to be the case that we'll see in terms of an alkyne, a triply bonded hydrocarbon, like that. 2 electron groups around the central carbon, or on both carbons in fact, one group here and one group here. That tells me that that carbon is sp2 hybridized. And so when I look at those bonds, this bond, and we usually draw it as the middle one, but it doesn't really matter. The first bond of a multi-bond set here, those are, and in fact this one over here too, those are my sigma bonds. Those are my first bonds between each pair of atoms. And those are, just like we saw in the other cases, the result of an overlap between hybrid orbitals. And hydrogen's 1s, because that's all it's got. In the middle, that sigma bond, right, is going to be carbon's sp overlapping with the other carbon's sp hybrid orbital. And in this case, I have 2 pi bonds, right? I've got the second and the third bond here. Those are both pi bonds, right? And I've got 2 of them in this case. Those are the result of carbon's p orbital overlapping with the p orbital. Or I guess to keep my language consistent, I said before it was a 2p. I'm only labeling it that way because that's typical for the atomic orbitals, the ones that we haven't really hybridized, is to keep that first number in there to indicate that it's a level 2. So this molecule has 3 sigma bonds, the hydrogen to carbon, carbon to carbon, and carbon to hydrogen, that are involving the carbon's hybrid sp orbitals. And I've got 2 pi bonds that are involving the leftover carbon atomic orbitals, those 2p orbitals that are left over. Same kind of thing would be true if we talked about something like, let's say, hydrogen cyanide, which looks like that. Okay, so I'll put this over in a little side thought bubble over here. So we know hydrogen, that's the easy one, right? Only 1s, that's all it's got. Now the central carbon, and in fact the nitrogen, how many groups of electrons do I have? Well, for carbon, I have a single bond and a triple bond. That's 2 groups. So that's going to tell me that carbon is sp hybridized. I only need 2 hybrid orbitals here, sp. What about nitrogen? Well, nitrogen has a lone pair of electrons over there and a triple bond over there. So again, 2 electron groups gives me sp hybridization. And so now when I talk about the types and characters of the bonds, I can say, I use the same coloring as before, the first bonds between each one I know are involving those hybrid orbitals. So this one is hydrogen's 1s because that's all it's got, and carbon's sp, one of the sp hybrid orbitals. And this one is a carbon hybrid orbital, sp, with nitrogen's sp orbital. The lone pair of electrons, likewise over here, is in nitrogen's sp orbital. And now my second, right here, and third, right there, those bonds are pi bonds, right? I have 2 of them. And those are between carbon's atomic 2p orbital and nitrogen's atomic 2p orbital. I've got 2 of those. So what's really great about this is that it allows us to really think about where the electrons are, and it allows us to explain not only shape, but reactivity. As I mentioned, when we talk about a molecule like ethine on the left here, this C2H2 molecule over here, we're going to see lots and lots of reactions that it undergoes. And in most cases, those reactions are the result of using or putting to work those pi bond electrons because they're a little bit higher in energy. They're a little bit more accessible. We'll talk about more of that later. But as far as hybridization, this is the end of the story. So for organic chemistry, what we're talking about is having 4 electron groups around a central atom. In Gen Chem, we would have used the description to say it's a tetrahedral framework or a tetrahedral electron geometry. And now we're going to say that when we talk about hybridization, that atom is sp3 hybridized. If we had only 3 electron groups, now we would have used the wording that it's a trigonal planar electron geometry. I will say sp2 hybridized. And when we talk about only 2 electron groups, we would have used the description of being linear. That's sp hybridized. Now, if you were to go on into some more complicated molecules, some period 3 or bigger, or if you were to go into like an inorganic chemistry kind of thing and start looking at more than 4 bonds to a central atom, you may remember from Gen Chem that there are some instances where you can get 5 or 6 bonds to a central atom. There's also hybridization talk around that, but I'm not going to get into that now because it's not relevant to organic chemistry so much. We're going to be focusing on these 3 types of hybridization, sp3, sp2, and sp. And in my mind, the best way to do that is to look at a molecule, decide how many electron groups it has, and then use that to dictate what types of bonds and hybrid orbitals you have. This all takes practice, so get to work, do some practice, and let me know how I can help. Good luck. Take care, everybody.